This is the so-called Poisson distribution. So there's something about this energy eigenstate that they're Poisson distributed in a coherent state. So these are probabilities, as I claimed, probabilities to find in n, and indeed, let's check the sum of the Cn squareds from n equal 1 to infinity. Let's see what it is. And you will see you cannot tinker with this. This is e to the minus lambda, the sum from n equals 1 to infinity, lambda to the n over n factorial. And that sum, it's not from n equal 1, it's 0 to infinity, I'm sorry. Did I write once anywhere? Yeah, should be 0. Okay, this is 0. There is the ground state. From n equals 0 to infinity, and this is e to the minus lambda, e to the lambda, which is 1. So yes, this is Poisson distributed. It's some sort of distribution like that. So if you have the n's, the Cn's, they're Poisson distributions have to do with if you have a radioactive material, it has a lifetime, and you say, how many events should the lifetime is 5 years. How many events should you expect to happen in a week? These are Poisson distributed. It's a Poisson distribution. It's a very nice thing. So let me make one more remark about it. And it's quite something. So one question that you could ask is, what is the most probable n? That's a good question. You have a coherent state, so it's going to have the superposition of the vacuum, the first. What is the most probable n? So the expectation value of n. Now, I'm thinking of it probabilistically. So I'm thinking this is a probability distribution. Then I will show for you that this is really computing what you want. But probabilistically, what is the expectation value of n? You should sum n times the probability that you get n. So this is sum over n, e to the minus lambda, lambda to the n over n factorial. So you got an n there. And the way you get an n there, well, the e to the minus lambda goes out. And the n can be reproduced by doing lambda dd lambda on the sum. Because lambda dd lambda on this sum brings down an n, puts back the lambda, so it gives you the thing you had. And that's what it is. So here you get e to the minus lambda, lambda dd lambda of e to the lambda. And that is lambda. Okay. So the expectation value of the most, sort of not the peak, but the expected value of n in this distribution, the level that you're going to be excited is basically lambda. So if x0 is 1,000 times bigger than d0, you've moved this thing 1,000 times the quantum uncertainty, then you're occupying most strongly the levels at 1 million. You get x0 over d0 controls which n is the most likely. Indeed, look, this n, suppose you would compute x0 tilde n hat x0 tilde. This is what you would think is the occupation number. This sounds a little hand-wavy, but this is the number operator, the expected value of the number operator in the coherent state. But this is, you have that the coherent state is this. So let's substitute that in there. So you got two sums over n and over m, and you would have Cm star m n n Cn. I've substituted x0 and x0 dagger. The c's, in fact, are real. And then the number operator on here is little n, and then you get the Kronecker delta. So this is sum over n and m, Cm, Cn, it's real. And then you get n delta mn. So this is, in fact, the sum over n Cn squared. So what we wrote here, this is really the expectation value of the number operator. And one can do more calculations here. A calculation that is particularly interesting to discover what these states look like is the uncertainty in the energy. So that's another sort of relevant measure. How big is the uncertainty in the energy? Like, what are basically the delta E associated to the coherent state? How does it look like? Is it very sharp? Is it? So it's a good question, and it's in the notes. I leave it for you to try to calculate it. Delta E in the coherent state x0. How much is it? And it turns out to be the following. H omega x0 over square root of 2d. So actually, maybe this is a little surprising, but delta E over H omega is equal to x0 over d. So actually, the energy uncertainty for a classical looking coherent state, I'm sorry, I'm missing a square root of 2 there. So what is a classical looking coherent state? It's a state in which x0 is much bigger than the quantum d. So x0 much bigger than d. So in that case, this is a large number for a classical state. But in that case, the uncertainty in delta E is really big compared to the spacing of the harmonic oscillator. So you have, here is the ground state, here is H omega, here is the coherent state, maybe, and you have a lot of energy levels that are excited. So if x0 over d is 1,000, well, at least 1,000 energy levels are excited. But you shouldn't fear that too much, because at the same time, the expectation value of E over delta E, the expectation value of E is something we calculated at the beginning of the lecture. You have the oscillator displaced. So this is roughly 1/2 m omega squared x0 squared. Throw away the ground state energy. That's supposed to be very little. Delta E is h bar omega x0 over square root of 2. And this is, again, the same ratio. So yes, this state is very funny. It contains an uncertainty that measured in harmonic oscillator levels contains many levels. But still, the uncertainty is much smaller by the same amount than the average energy. So this state is a state of some almost definite energy, the uncertainty being much smaller, but even though it's much smaller, it still contains a lot of levels of the oscillator. So that, I think, gives you a reasonable picture of this, so you're ready for a generalization.